In this type of architectures, the components of a software system communicate together by producing and consuming events. This is different from other architectural styles such as API-based architecture, where components of the system send requests to other components of the system and wait for a response, making the communication synchronous. In event-driven architecture, producers of events simply send out the event and do not care who the consumer is and if it has processed it or not. They simply move on to their next task, making the communication asynchronous. Event-driven architectures consist of three essential components: the event producer, the event router, and the event consumer. The event producers generate events, which are essentially messages, usually in JSON format, that are then ingested by event routers and distributed to event consumers that are interested in receiving the events. In an event-driven architecture, you may have any number of event producers and event consumers. The components are loosely coupled and can be scaled independently. Some examples of events are user actions, such as clicking a button on a website. It can be data update in a database, or it can be any type of system change. Now let's look at some of the benefits that event-driven architectures provide. The loose coupling of the components provides very important benefits such as scalability, because it is possible to increase the number of instances of a single system component if we know that this component is getting additional load, without actually increasing the number of instances of any of the other components. This is called horizontal scaling or scaling out of the components. Another very important benefit of event-driven architecture and the loose coupling of the components is fault tolerance. Because producers don't know about consumers who consume their events, and consumers don't know about the producers, they only know about the events, then if one component, for example, on the consumer side fails, then all of the other components of the system keep working as usual. Producers will keep producing events, and other consumers will keep consuming events. There are also patterns that can be used to ensure that the failed component will still have access to the events that it has missed while it was down once it comes back up. Those patterns involve things like persistent storage in the event streaming architecture. Another great benefit coming from the decoupled nature of the architecture is maintainability. It is possible to maintain or to update a single component without affecting how the rest of the components of the system are functioning. Other benefits of this type of architecture include the fact that new components can easily be added to the system. Also, asynchronous messaging means that producers don't need to wait for consumers to acknowledge that they have received an event. Also, each component has its own independent view of the system. As we mentioned earlier, producers don't necessarily know about who the consumers are, and consumers vice versa only know about the events and not the producers. Also, this architecture allows real-time event processing, as consumers can respond to the events as soon as they arrive. Now let's look at the patterns in event-driven architecture. There are patterns concerning the different aspects of the architecture, including event generation, communication, error handling, consumption, etc. Now, it would be out of scope to go over each one of the patterns. I'll just mention the ones that are most often used. So, one of the most often used patterns is publish-subscribe. Publish-subscribe means that consumers of events subscribe to receive certain types of events, and they get notified when this type of events arrives. Another important pattern is event streaming. In event streaming, unlike publish-subscribe, the consumer does not subscribe to receive the events. Instead, the events are written in a log, and the consumer can go inside the log and read the events starting from any point in time that it likes, and it is responsible to move through the stream of events on its own. The next pattern that I want to talk about is in the consumption area. So, unless you implement something to guarantee delivery, there is no guarantee that an event that has been fired by a publisher will be received by the subscriber or the consumer. So there are different patterns you can use to guarantee that the event is either received only once, at most once, or at least once. And the last one I want to talk about in this section is inside the consumer scalability area. So this one is called competing consumers. What happens is that if you want to scale one of the consumer components in order to process events in parallel, you need to ensure that once an event is processed by one of the scaled instances of the consumer, it will not be processed by any other of the instances, so it's not processed more than once. Now let's look at some of the anti-patterns that we should be aware of when developing event-driven architectures in order to make sure that our architecture is as efficient and as useful as possible. The first one I want to talk about is the dependencies between events. So it is important to remember that events should be atomic and should not implement any sort of dependencies to other events. The next anti-pattern is assumed knowledge. Assumed knowledge is the idea that a producer should not know about who the consumers are and how they process the messages or the events that it produces. So events should be self-contained and sufficient for any type of consumer to understand what the event is. For example, if a website generates an event about a new order that the customer has just placed, the message contained in the event should tell everything to a consumer about that new order, who the customer is, what the order is all about, when it was placed, etc. So it doesn't matter who the consumer is, they have everything they need to understand what the event that just happened is. The next one that is important to know is generic events. So this refers to the idea that events should be specific and linked to a specific business process. There should not be confusion about which business process this event refers to. For example, a new order has been placed. The last one I'm going to talk about is implementing a sequence. So implementing a sequence such as event 1 should be followed by event 2 coming from the producer is not the correct thing to do in event-driven architecture, because you're assuming the way or the order in which a certain consumer is going to process those events. Events should be isolated from each other. So there are patterns that exist for coordinating events, such as the orchestration and the choreography patterns that should be used in cases where you need to coordinate sequences between the events, but this is not happening on the producer side. The next topic I want to cover is how event-driven architecture and microservices work well together to offer the benefits that we expect from modern software architectures. So you can think about microservices as the structure or the way you structure the components of a system and its subsystems. And the event-driven architecture is how those components can communicate together. Both of those concepts offer loose coupling between the components that allows a lot of the benefits that we get, such as scalability. As I mentioned earlier, we can take one of the components that we know is experiencing a superior load compared to the others and spin multiple instances for that component only without scaling the entire system. We also have the flexibility and adaptability, because a particular component of the system, let's say a particular consumer does not know about the producers and vice versa, we can simply remove that consumer or that producer and replace it with something else that continues emitting the same type of events or consuming events without affecting the system. And the last one is the complexity and the challenges that both of those concepts are sharing. Essentially, when you have a distributed system, you have many components to look after, many events happening all throughout the system that you need to keep track of. Also, handling failures become more challenging, and ensuring consistencies between events becomes a challenge as well. All in all, there are many conceptual similarities between the two types of architecture. Now that we covered the concepts of event-driven architecture, let's look at a real-world example, which in this case is a retail company. The retail company has points of sale, which are physical stores with cashiers, They have a mobile app where you can go and purchase items, and they have an e-commerce website where you can go and do things like rating articles, writing reviews, or even purchasing. On the other side, they have a payment system that manages the payment transaction, returns and all that. They have a customer support system and a warehouse management system. So if a customer goes to a point of sale to return an item, then a return event is generated. This goes down to the event router. If somebody else goes to the mobile app and purchases something, we have a new order event generated that goes down to the event router. And then if we have an e-commerce website user who goes and writes a review about the product that they purchased, we have a product review. So all of those events that are being generated here, they're unrelated, done by unrelated people, and they go down the event router, which ingests the events. And then we have systems that are subscribed to the event router to receive the types of events that they're interested in. For example, we have the payment system that's interested in knowing if there is a return occurring and if there is a new order, for example. So those two events will be passed down to the payment system so they can process those types of transactions. There's the customer support system that's interested in the product reviews that the client has placed, so they receive that event. And then we have the warehouse management system, which receives new orders and returns so they can adjust inventories. So all of those systems, as you can see, they're decoupled from the other systems that the customers interact with. They receive the events that they're interested in and they process those events. In terms of the technology stack used to implement event-driven architecture, I'm going to look at the core technologies used for this and the cloud implementations that some of the biggest clouds are providing, such as Azure and AWS. So in terms of core technologies, you should definitely be aware of Kafka. Kafka is a distributed event store and stream processing platform. The most important thing about this is that it is a very high throughput and low latency platform for handling real-time data streams. This is an open source project that is owned by the Apache Software Foundation, and Kafka is actually used as the basis for a lot of the implementations provided by the clouds. So you'll see a lot of mentions of Kafka if you start looking at different implementations in the clouds. Another important core technology is RabbitMQ. RabbitMQ is a message broker that used to be an implementation of the advanced message queuing protocol only, but since then it has expanded into different protocols and supporting many additional use cases. So you should know that at the basis Kafka and RabbitMQ were developed to address different use cases. But as RabbitMQ is expanding its capabilities, it's becoming to some extent interchangeable with Kafka in some cases, but you should still consider what you're doing. If you need really high throughput, Kafka is usually the best option. So on the Azure side we have the Event Grid. The Event Grid is a fully managed service that supports routing of event by utilizing the publish-subscriber model. Next we have the Service Bus. The Service Bus and the Event Grid are similar because they both use the publish-subscriber model to manage events. The difference is that the Event Grid is based on a pushed mechanism, so it will push the events to the consumers, while the Service Bus uses a pull mechanism, so the consumers are pulling events from it. Then we have the Event Hubs. The Event Hubs is different from the two others in that it is focused on a very high throughput, so it's especially useful in applications involving IoT, Internet of Things, where you have an extremely large number of events coming through it. So it's less focused on the routing and more focused on the throughput. And the last one for Azure that I want to cover is the storage queue. The storage queue is a service for storing large numbers of messages that can be accessed through internet using the HTTP and HTTPS protocols. Then moving on to AWS, we have the event bridge. The event bridge can be used to route events from sources that can include anything from customer applications to AWS services to third-party SaaS to consumer applications. We also have SNS. SNS is a simple notification service. It can be used to deliver messages in strict order, such as first in, first out. This is the end of my review of the tech stack. There are definitely more implementations. My goal here is not to cover them all, it would be out of scope. It's just to give you some idea about what is out there. If you enjoyed watching this video, don't forget to like and subscribe so you can see more of this type of videos in the future.